In this video, we're going to be discussing the first law of thermodynamics. And whether you realize it or not, you're probably already familiar with the idea of this law, because most people aren't introduced to it for the first time by name, but rather by the idea or the phrase that energy can be neither created nor destroyed. So this is kind of the non-scientific phrasing of this. But it gets the point across. So the way we like to phrase this a little bit more quantitatively is that the total energy content of the universe is constant. So these two phrases mean the same thing. That in the universe, there is a fixed amount of energy. We cannot create more. We cannot get rid of any. The total amount of energy present in the universe at any given moment is always constant. So you'll sometimes see this phrased mathematically as delta E universe equals 0. Remember that the delta always means change. So this is just saying that the change in the energy of the universe is always 0, that no matter what you do, no matter what happens in the universe, the total change in energy is always 0. We're never gaining energy, we're never losing energy overall. So what this means for us on a smaller scale is we're usually studying some system, and that system can have an effect on its surroundings, or the surroundings can have an effect on the system. And that those two things, the system and the surroundings, are the only places that energy can travel in the most general sense. The first law of thermodynamics tells us that all energy gained by the system must have come from the surroundings. And all energy lost by the system must go to the surroundings. So this also allows us to expand our use of the equation that we've been using to calculate heat. For a chemist, energy and heat are largely interchangeable. So I will often use those terms interchangeably since the only energy we are dealing with is heat. But we can take that same Q equals mc delta T equation, and if we know that any heat lost by our system must go into the surroundings, we can now say that the heat transfer of the system and the heat transfer of the surroundings have a relationship. And this is going to allow us to apply the same equation to a lot of different situations. So if we know that any heat lost by my system has to go into the surroundings, if my system loses 100 joules of heat, the surroundings gains 100 joules of heat. If my system gains 50 joules of heat, the surroundings must have lost 50 joules of heat. So the heat changes, the heat transfers of the system and the surroundings are always equal and opposite. So we can say that there is this relationship between them. Q system equals negative Q surroundings, or the opposite of Q surroundings. The number of joules, the amount of heat transferred, is going to be the same, but the direction is different. One loses, the other gains. We can apply this further if we know that Q system is negative Q surroundings. We also know that Q equals MC delta T. So we can sub in this expression of mass times specific heat times temperature change for either one of these Qs or both of them. So you'll sometimes see the expression Q system equals negative M surroundings, C surroundings, delta T surroundings, where we've taken this expression and subbed it in for this Q. You will also sometimes see M system times C system times delta T system is equal to negative M surroundings, C surroundings, delta T surroundings. So we've subbed MC delta T on the right and MC delta T on the left. So we can use this equation and these two relationships together now in a bunch of different ways that we can relate our system and our surroundings. Either if we know the heat of one, we can relate that to the mass specific heat and temperature of the other, or we can relate the mass specific heat and temperature change of the system to the mass specific heat and temperature change of the surroundings. And those are the same thing. So in using these, we need to know something about both our system and our surroundings. But if we think about our definition of surroundings, that seems a little problematic. The thermodynamic definition of surroundings is literally everything in the universe that is not part of our system. So how do we measure that? And the answer is we don't. So what we do is we essentially create a mini universe that we are assuming to be isolated from everything else. So this is where we're assuming an isolated area that all of our heat transfer is occurring within. And we call that, or the device we use to do that is known as a calorimeter. So you'll be using a calorimeter in the lab that you're doing this week. So it's just some kind of insulated container that is used for thermodynamic experiments. And whenever we're doing calculations involving a calorimeter or a calorimetry experiment, we're assuming that everything inside the calorimeter is isolated from the rest of the universe, that no heat transfer occurs into the calorimeter or beyond it. So this is not quite true, but it's usually close enough that we can get pretty good results. And there are different types of calorimeters that you can use, varying in degrees of sophistication. The ones that you'll be using are basically fancy styrofoam cups. They're extra thick styrofoam cylindrical-ish containers that are pretty darn well insulated, that they don't absorb a lot of heat themselves. They don't let a lot of heat escape beyond them. So they work pretty well and they get really good results. So by insulating a small portion of the universe, we can just make measurements inside our calorimeter and define a system and surroundings within that space, even if we need to. So applying the first law of thermodynamics is going to allow us to solve more complicated problems involving more than one different substance. The things we've looked at so far have just been, here's some water, it's cooling off, what's the heat transfer? But in a chemical reaction, we're usually dealing with heat being released to the surroundings or absorbed from the surroundings. And it's usually really the surroundings that we're measuring. So we need to be able to relate surroundings to our actual system, relate the heat transfers in two different substances, which is why the first law of thermodynamics is really critical to us. We'll be applying that in essentially every situation that we're calculating the heat transfer in a reaction. So still starting relatively simple here, not looking at a chemical reaction just yet. We can solve something like this, where we have two different substances. In this problem, it's silver and water. We're taking a block of silver, specific heat is given, at 185 degrees Celsius, and dropping it into a calorimeter containing 50 grams of water at 25 degrees Celsius. Specific heat is 4.184. Sorry, forgot to write that in. After the contents of the calorimeter reach thermal equilibrium, meaning after everything is the same temperature, the temperature of everything inside is 29.5 degrees Celsius. And we're solving in this case for what was the mass of the silver block. Not the most useful way to apply this, but it's a way you could apply this. So essentially we have heat being transferred from the silver to the water. In this case, we have hot silver going into relatively cool water. So we're doing this in a calorimeter, so we're assuming that all of the heat transferred from the silver goes into the water, meaning that Q for the silver is equal to negative Q for the water. So we're assuming all heat lost by silver is gained by the water. And there's no loss, no heat goes anywhere else. Again, this would not quite be true in practice, but it would be a good enough approximation that we should be able to get pretty darn good results from this. So in this case, we know the specific heats and masses, we know the specific heats of both of our substances. We know the temperature change that happens in both of our substances, and we're looking for one of the masses. So if we plug in MC delta T on both sides, we just need to keep track of what mass, what specific heat, what temperature are we talking about, and the M, the C, and the delta T for the same substance need to stay on the same side. So we will have the mass of the silver times the specific heat of the silver times the temperature change of the silver is equal to negative mass of the water times specific heat of the water times the temperature change of the water. So if we think about what we know from the problem, we're looking for this information about the silver and that same information about the water. So if we look back in our problem, we've got the specific heat of silver given to us here. We have the initial temperature of the silver, and we have the final temperature of both the silver and the water, both colors, I guess. Then we've got the mass of the water, specific heat of the water, and the initial temperature of the water. So what we know is the mass of the silver is what we're solving for. That's the one thing we're not given. Specific heat of the silver is 0.24 joules per gram degree Celsius. Delta T for the silver. This was our final temperature. This was our initial temperature. We always want to do final minus initial. Gets us a delta T of negative 155.5 degrees Celsius. And then on the water side of things, the mass of water was given as 50 grams. Specific heat of water is 4.184 joules per gram degree Celsius. And then the change in temperature of the water. Final temperature was 29.5. Initial temperature was 25. Gives us 4.5 degrees Celsius temperature change of the water. So in a case like this, you should always find one of the temperatures increased and one of the temperatures decreased. Otherwise, it's not going to work. You put a hot thing into a cold thing, they meet in the middle. So something has to increase, something has to decrease. If not, double check your final minus initial on your temperature changes. So at this point, we can just plug into our equation. We've only got one unknown thing, and we'll be able to solve for that. So we have mass of silver times the specific heat of silver was 0.24. The temperature change of the silver was negative 155.5 degrees Celsius is equal to negative, don't forget that negative sign, that has to stay throughout. The mass of the water is 50 grams. Specific heat of water is 4.184 joules per gram degree Celsius. And then the temperature change of the water was 4.5 degrees Celsius. So we can divide both sides by C delta T of the silver in order to solve for our mass. And the mass of the silver block comes out to about 25 grams. Note that we are limited to 2 significant digits in our answer because you were only given 2 significant digits in the specific heat of silver. So this is our limiting factor here. So we should round to 2 sig figs at the end.